Let me guess, when you take the SAT Math, you're thinking, damn, this test is so easy. I know how to subtract a number. But then you get to the end of module 2 and you see this, and you realize that you actually don't know how to do math, and you're not getting into college, and you've disgraced the last 25 generations of your family. Don't worry, I have good news. Almost every single hard problem on the SAT falls neatly into one of 25 question types. And if you understand every one of these 25, you will get a near perfect score. So I wrote up all 25 of these problem types, and you can download this PDF completely free with the link in my description. And in this video, I'm going to walk through 10 of those 25 problems. So without further ado, let's begin. We have a problem where we're solving for coefficients, where we have this expression equal to this expression, and we're trying to find the value of a plus b plus c. This is a setup that the SAT really likes, and their goal is that you have to algebraically rewrite the right-hand side to be in the same form as the left-hand side. So specifically, we're trying to get a common denominator, and then we're going to distribute these, and then we're going to combine like terms. And this is what it looks like if you were trying to do that. It's not pretty, but the good news is that we can actually solve this using Desmos with a regression. So you might understand a regression as fitting a bunch of points to a line. Like imagine we have the points 2, 5, and 3, 7. If I run a regression on this, Desmos will tell me that the equation connecting these 2 points is 2x plus 1. But you can also, with Desmos, specify a function, like maybe this function right here on the right side, and Desmos will arbitrarily choose points on that function and then fit the coefficients a, b, c, and d to those points. So let's look at this for a much simpler example. Let's say we have ax plus b equals 2x plus 3. And I'm sure all of you can tell that a should be 2 and b should be 3, but let's have Desmos figure this out for us. So we can split this into two different functions, ax plus b and 2x plus 3. And now we want Desmos to come up with points on this line and fit a and b such that ax plus b connects those points. So the way we're going to do this is we're going to type f of k, or any letter we want. This could be E, this could be H, this could be J, this could be X1, whatever we want, as long as we're inputting some constant. So we can't put X in, and we don't want to put A and B because we've already specified A and B. So f of some constant k has to be fit to g of some constant k. And so what Desmos is going to do is it's going to pick some value for k, in this case k equals 1, and it's going to make sure that f of x and g of x are equal at k equals 1, which sure enough we see they are. The problem is a equals 4 and b equals 1, even though they work for k equals 1, they don't work for any other k, right? And so our red line, the left-hand side, and our blue line, the right-hand side, are not actually the same. So we need to tell Desmos, don't just find values that work for k equals 1, but also find values that work for k equals 2, or any other point. I could have made this point 3 or 5 or pi or 1 million, right? We just want Desmos to find an a and a b value that makes ax plus b fit 2x plus 3 at the points 1 and 2. That's what all this is saying. And so we can apply this setup to this problem as well. I recommend you pause and try this on your own if you haven't already, but now I'm going to show you how it's done. So first we want to set f of x equal to the left-hand side. As a little Desmos trick, if you have a fraction bar, just do your fraction bar at the start before you've written any of the terms, so that you can easily write everything in the numerator, then just hit the down arrow and then do everything in the denominator. So we have x squared minus 9 times x plus 2. And then we're not going to create a bunch of sliders because that would be terrible. We don't want to slide things around. We want Desmos to figure out these values for us. Then we're going to type in g of x and do 5 over x plus 6x over x minus 3. And now we want to run a regression, so let's do f of k regressed on g of k. And sure enough, it's picking values for a, b, c, and d that work at k equals 1. But once again, as we can see graphically, the purple and the red are not fit to the same function. They work at k equals 1. We can see f of 1 is negative 1.5 and g of 1 is negative 1.5, but they clearly don't work at every single point, and so we want to specify more points. So first, if I specify 1 and 2, we see this still isn't working. And the reason for that is we have 4 different parameters that we're trying to estimate. So 2 points is not enough. We need 4 points, because what's actually happening under the hood is Desmos is constructing systems of equations and trying to optimize those. And so if each of these points gives us a different equation and we're trying to solve for 4 different parameters, we need 4 different equations, which means we need 4 different points. So let's go with 1, 2, 3, and 4. So now we have 4 different points, but the problem is Desmos clearly doesn't like this. And it doesn't really tell us why explicitly, but Think about what happens if you plug in 3 into these functions. For g of x, you get 3 minus 3, which is a denominator of 0. And in f of x, you get 3 squared minus 9, which is also a denominator of 0. And this is problematic because it's trying to fit something that's undefined to something that's undefined. It can't do that. And so we're going to replace 3. Let's do pi just for fun. So now we have Desmos making sure that at the points 1, 2, pi, and 4, f of x and g of x line up. And when it does that, it finds these values for a, b, c, and d, which sure enough are the correct values. So the problem asks us to find a plus b plus c. We do a plus b plus c, and we get 72. Is this a long process? Yes. But I think for a function as complicated as this with 3 or more coefficients that we have to solve for, this is going to be as fast or slightly faster than doing it by hand. And more importantly, it's going to be a whole lot more accurate. It is much harder to make a mistake here than if you're doing this by hand, right? Like very clearly I can see that f of x and g of x are the same thing with these a, b, c, and d values. Versus if you do it by hand, plenty of room for error. Now, you might be thinking percentages are easy, I can do percentages, but there are a lot of ways that College Board tries to get you with these types of problems. So let's read this one. A is 540% more than B. So the first thing is if you wrote down A equals 5.4B, that would be incorrect because 540% more than B means we are taking this quantity, 540% of B, and we're adding it to B. So another way of writing this would be A equals 6.4B. This is what I want you to get in the habit of doing, is whenever you see some percentage more than, you just add 1 to that number as a percentage. So A equals 6.4B, and B is 0.02% of C. A lot of people are going to write that like this, but that is wrong. This would be 2% of C. When we convert a percentage into a decimal, you move the decimal place 2 spots over, or you can think of it as dividing by 100. So we should have 0.0002 times C. So let's just add in those extra zeros now. If A is k% of C, then what must K equal? So we can say A equals K over 100 times C, because K over 100 represents k% as a decimal, and when we multiply the decimal by C, we're getting k% of C. Like imagine if K were 70, then this would be 0.7 C. 70% of C. So then the question is, how are we going to solve for K? Because we have 2 equations given to us and 3 unknowns. So clearly we can't find values for A, B, and C. However, we don't need to find values for A, B, and C. Really what we want is we want an equation that gives A equals some number times C. And as long as we have that number, we can equate that number to K over 100 and use that to solve for K. So how do we do that? Well, if we want A equals something C, which constant do we need to eliminate? B, right? And we can eliminate B by substituting 0.0002 C in for this B. So we get A equals 6.4 times 0.0002 C. Then I can pull out my TI-84 and do this multiplication, and I get A equals 0.00128 C. So now I've rewritten this equation to be in the same form as this equation up here, which allows me to simply compare the coefficient K over 100 with this coefficient 0.00128. And so I can say K over 100 equals 0.00128, and by multiplying by 100 on my calculator, I get that K equals 0.128. So that's my final answer. Okay, brief intermission. Y'all keep saying I look like Linguini from Ratatouille. Quite frankly, I don't see the resemblance. We look nothing alike. You guys just think every French person looks the same. It's kind of racist. Anyways, if you thought the first 2 problems were very challenging, but you're trying to get a 750 or higher, I highly recommend you join my SAT Math Masterclass. It's a small group class where you'll be with a couple of students and myself. We cover every single hard concept and problem on the SAT Math. It is a difficult course, but you will come out the end of it being able to solve every single problem in this video. And most students who have taken the class end with a 750 or higher. That is top 1%. So head over to LearnSATMath.com. I'd love to work with you, and I do not look like Linguini. Zero resemblance whatsoever. Next up, we have an integer constant problem. So first, let's define what an integer is. An integer is a positive or negative whole number, or 0, right? So -2, -1, 0, 1, 2, etc., etc. 3 over 2. Fractions are not integers. 1.5 decimals are not integers, right? They have to be whole numbers. And so we're told that h, k, q, and z are all integer constants and asked which of the following must also be an integer. So we really don't have a lot to go off of, but we know that this side, the two binomials, has to equal this side, the trinomial. And so it's going to help us a lot if we multiply this binomial out using FOIL to compare the coefficients. So we get hq x squared. A stupid dishwasher. I get it, bro. You're done washing the dishes. This is not a big deal. So if we use FOIL to multiply everything out, we get hqx squared plus kqx plus kz equals all of this. And then if we combine like terms, we get hqx squared plus kq plus hzx plus kz, right? And now we can clearly identify that hq has to equal a, kq plus hz has to equal b, and kz has to equal 35. So for the sake of simplicity, I'm going to rewrite these three comparisons as their own equations. And let me just get rid of all this, and we can work just from these three equations. So the first thing we're trying to evaluate is 35 over k. Is this an integer? Or rather, does this have to be an integer? When these problems have been asked on previous SATs, this is what you care about. You care about whether the constant term divided by one of these integers has to be an integer. And the answer, historically, is always yes. At least this is the way that the SAT has tested it. Don't try to memorize the shortcut, but it's worth telling you that this is generally how this topic is tested on the SAT. And we can use this equation to prove this. If kz equals 35, then 35 over k is just equal to z. And we already know that z is an integer, which means 35 over k has to be an integer as well. And so if you see this on the SAT, the first thing you should check, if you have A, B, C, D, check this one first. Check the one that is the constant divided by an integer, because chances are you just use this last equation and you get the answer very easily. Okay, now onto number 2, we have b. So first we need to think about what happens to integers when we add them together or multiply them together. If you take two integers and you add them together, sure enough, you do get another integer. And you can just think about this to yourself. Think, can I take two integers and add them together and get a decimal? The answer is no, right? There's no way that you can add two whole numbers and get a non-whole number. Same thing with multiplication. An integer times an integer does indeed have to give you an integer, right? But now think about an integer divided by an integer. Does that need to give you an integer? Hopefully you've thought about it. It does not, right? Easy example, 1 over 2. 1 is an integer, 2 is an integer, 1 over 2 is clearly not. So kq plus hc, that's just a bunch of integers added and multiplied together. So sure enough, the sum of their product is also going to be an integer. So we can say the 2 also has to be true. Finally, we have negative a over q. We're going to approach this very similarly to how we did number 1, where we have hq equal to a. We can rewrite this as h equals a over q, and then we can multiply both sides by negative 1 to get negative a over q. This one's maybe a little less direct, because we're not told that negative h is an integer, we're told that positive h is an integer. But think back to the multiplication of integers. If you multiply negative 1 by h, that's just an integer times an integer, which means negative h has to be an integer. You can also just think to yourself of examples like, let's say h is 7, then negative h would be negative 7. That's always going to be an integer if you just take a negative counterpart of a whole number. So sure enough, all 3 answer choices have to be integers. And that's the end of problem 10. Moving on to problem 11, this is one of my favorite ones in this entire document. It's also one of the hardest. So we're given this quadratic function in standard form, and we're told that f of negative 4 equals f of 8, and you have intercepts at these points r and s. And which of the following must be true? And it seems very intimidating that we're supposed to derive all of this just from going off our a value being negative 3 and f of negative 4 being f of 8. The key to approaching these problems is to know all of your quadratics formulas. And I go over where all of these quadratic formulas come from in my book, SAT Math from the Ground Up. There's also a slightly more condensed explanation in my video, All the SAT Math in 27 Minutes. And so I'm going to pull a bunch of formulas in this explanation, but you should have these memorized and understood on your own first before approaching a problem like this. So when you see f of negative 4 equals f of 8, your mind may go, oh, maybe I should plug negative 4 into this function and plug 8 into this function and see what happens with that. But that's actually not the reason they're telling you this. When the SAT tells you that f of some point equals f of another point, they're telling you where the vertex has to be. Because think about this. If you have a parabola where 8 and negative 4 are at the exact same y coordinate, the vertex has to be exactly halfway in between those points because parabolas are perfectly symmetric about the vertex. So this point right here has to be at 2. We can do this by doing -4 plus 8 divided by 2, and we get 4 over 2, which is 2. So this is telling us our h value, right? The x-coordinate of the vertex has to be 2. And if you look at number 1, this seems completely unsolvable, right? Like r plus s, these are the two x-intercepts, but we have no idea where those x-intercepts are. Sure enough, we can actually solve this now that we know that h equals 2. How? Well, r plus s, we have no idea where they are, but we know that the midpoint between these two x-intercepts has to be the vertex, has to be 2. So we know that r plus s divided by 2 has to equal 2. Therefore, r plus s has to equal 4. You can also just memorize the relationship that the sum of your solutions is 2 times h. But I think it makes more sense to think of it as the midpoint because that sort of connects it to the graph as opposed to this like very abstract formula that doesn't make much sense intuitively. So next we want to evaluate whether b is less than 0. And there are actually 3 ways that you can do this. So the first way is with this formula that h equals negative b over 2a. And so with this formula, we can plug in our a of -3 and we can plug in our h of 2 and we can use this to solve for b. So we get 2 equals b over 6. So b equals 12. And 12 is most definitely more than 0. Another way that you can solve this and also get b equals 12 is using the formula that the sum of your solutions is equal to negative b over a. And this just comes from combining the fact that h equals negative b over 2a with the fact that the sum of your solutions equals 2 times h. And you can think about on your own how we can combine these two equations to get this equation. But again, on the SAT, you should just like memorize this. We know that the sum of your solutions is 4 from answer choice 1. And again, a is -3, and so we get b equals 12 once again. And the third way to solve this is with vertex form, but I actually want to save that for answer choice number 3. So here we have answer choice number 3. There are 2 ways that you can think about this. The first one is getting a very concrete answer using vertex form. And the way that we can do that is writing this equation in vertex form. Vertex form is a times x minus h squared plus k. So we can plug in our a and plug in our h. And then if we multiply all of this out, we get -3 x squared minus 4x plus 4 plus k. This is -3x squared plus 12x minus 12 plus k. And so sure enough, from this, we've identified our a. It's the same a as we originally had. That's no surprise. But now we have a definitive value for b, so this could also be used to figure out answer choice 2. And we have a definitive value for c, where c equals k minus 12. And so then the question is k minus 12 less than k? Yeah, it is. So we can say answer choice 3 does indeed need to be true. And I'm just realizing that I put a check next to answer choice 2. That was a mistake. 2 is definitely wrong. B equals 12, which is not a negative number. Sorry about that. And so this is a very reliable way of getting the correct answer. Like if I put k minus 5 here, you would still be able to say, yeah, okay, c also has to be less than k minus 5. However, if we're just asked whether c is less than k or not, we can actually solve this graphically because k and c both can be easily spotted on the graph. K is the y-coordinate of the vertex, so it's like your maximum of the quadratic. And by the way, I know the quadratic is downward facing because our a is negative. If a were positive, it would be upward facing. And c is the y-intercept of the function. Think about this as if I plugged in 0 for x, I would get -3 0 squared plus b times 0 plus c. That means f of 0 equals c. So c is your y-intercept. That's always the case for any quadratic function. You should have that memorized. So if k is the maximum and c is the y-intercept and the function's downward sloping, we can see graphically that k always has to be above c. There's no way that you can have a y-intercept above the maximum point because the maximum is by definition the maximum. Now you might think to yourself, well, okay, what if I had a quadratic like this, where the y-intercept is the maximum of the function? Then your c can equal your k. However, we know that that's not the case here because your h is equal to 2. So the vertex is not centered at the y-axis, it's slightly off. So in conclusion, 1 and 3 are both true. And when the SAT asks this, they're maybe a lot more likely of only testing maybe one of these three things, not all three of them simultaneously, but I think it's good for the sake of this problem to test everything because you want to be able to use all of the formulas that I've talked about in this explanation. This is a problem type that the SAT has been asking multiple times pretty recently. 3 consecutive even integers are ordered from smallest to largest. So let's think about what this actually means. This means if we had like 2, 4, and 6, right? These would be 3 consecutive even integers, or maybe 10, 12, and 14. But if we want to write this more generically, we can say that our first integer is going to be x, the second one x plus 2, and the third one x plus 4. Because this is going to hold no matter what integers I choose. If I decide x is going to be 122, then sure enough, the next even integer is going to be that plus 2. And the even integer after that would be that plus 4. Okay, continuing on, we get 5 times the first integer. So that's 5 times x is at least. So that's going to be greater than or equal to, right? If it's at least, let's say 12, then that means we can be 12 or we can be above 12. So that would be a greater than or equal to sign. 9 more than something would be 9 plus that thing. The sum of the second and third integers, that's the sum of this one and this one. Those are the second and third integers in the sequence. So we can do x plus 2 plus x plus 4. So we're trying to find a minimum value for x plus 2. So first off, this inequality has just one variable and one inequality, which means we can isolate x. We get 5x is greater than or equal to 2x plus 15. Then we get 3x is greater than or equal to 15. And then we can divide both sides by 3 and get x has to be greater than or equal to 5. So if x can be greater than or equal to 5, then what's the minimum value of the second integer? You might be inclined to say, okay, 5 plus 2, so 7. Why would that be wrong? Well, we need even integers, right? So x has to be greater than or equal to 5 means that the smallest value that we can choose for x is going to be 6. And so therefore 6 plus 2 has to be 8. So 8 is the smallest possible value for the second integer given all of these constraints. Notice that the way that I approach this is I translated the words, the paragraph in English, like bar for bar into math. 5 times the first integer, 5x, at least, greater than or equal to, 9 more than, 9 plus. Like every single chunk of the text has a direct translation into mathematical terms. And you should be very comfortable translating it piece by piece like that. Don't read the entire sentence and then try to come up with the entire inequality. You will make a mistake. Next up, number 17. In triangle ABC, the measure of angle B is 90 degrees. AB is a leg with length 12, and segment AC contains a point D. D is not necessarily an altitude of the triangle. We'll talk about what that is in the next problem. But we know that there's some point D somewhere on this segment, and we don't know where. So which of the following must be true? The first answer says BC is equal to 12 times the tangent of angle CAB. So CAB is this angle right here up top. The tangent of CAB is the opposite side over the adjacent side, right? That's the TOA in SOHCAHTOA. Please, if you're watching this video, you better know what SOHCAHTOA is. So the opposite side is the side BC over the adjacent side, which is AB, which is 12. So this means that tangent of CAB equals BC over 12. If we rewrite that, we get that the tangent of CAB times 12 equals BC. So sure enough, this indeed must be true. The second answer asks if cosine ABD, so ABD, that's this angle right here, minus the sine of DBC, that's this angle right here, has to equal 0. This one seems maybe a little harder to evaluate because we don't actually know what ABD or what DBC is. For all we know, this could be 30 and 60, this could be 1 and 89. This could be, like there are a lot of different options here. We also don't have any right triangles that we can use the cosine and sine for. If this made a right angle, then maybe we could look at some ratios between sides, but this is not necessarily a right angle, and so we can't use side lengths either. What we can do, however, is use the formula that if we have two angles, call them A and B, that add up to 90, then the cosine of A equals the sine of B. And so once again, if you want an explanation of why this formula works, check out my book, SAT Math from the Ground Up. But you should have this memorized, that any two complementary angles, that's angles that add up to 90, the sine of one equals the cosine of the other. And so think about what this means. ABD and DBC, these two angles, are complementary. They do add up to 90, which means that the cosine of one of them is equal to the sine of the other. Like we can say, even though we have no idea what these angles are, we know for a fact that the cosine of ABD is going to be equal to the sine of DBC. And so sure enough, if you take two things that are equal to each other and you subtract them, you get 0, right? And the SAT has really enjoyed testing this formula in this specific way, where they ask about the difference between the cosine of one angle and the sine of the other, and you simply cannot solve this problem without knowing this relationship. Like, you just can't. And the answer is always going to be 0, because like that's the only way that you can invoke this relationship without actually knowing the angle measurements or having these be right triangles. So okay, we've proven the 1 and 2 have to be true. Finally, angle ABD, so that's going to be this one, equals angle BDC, so that's going to be that one. Do we know that this is true necessarily? Well, we do not. If BD were an altitude, like if this constructed a right angle, then we could indeed say that this angle and this angle have to be the same, because these two triangles would have to be similar, and they'd be similar such that those angles correspond to one another. However, when we have this unknown angle measurement, these triangles definitely do not need to be similar. Like, let me just plug in some values that seem plausible. We have 30, 60 right there. And then this one, I'm going to say is also 60. And this is 60. And then this one's going to be 30. And then this one's going to be 120. Like, this 60-degree angle and this 30-degree angle definitely are not the same. And you can see that by me plugging in a bunch of values. And so how would you actually prove this on the SAT? Well, I think if you have a good understanding of altitudes and why altitudes create a bunch of similar triangles, then it will make sense why this does not create similar triangles. But if you don't understand altitudes, this seems sort of arbitrary. I guess putting in values like this might help, but in practice, I think it's just, if you don't have a way of proving that something is true, then it probably doesn't have to be true. And so for this problem, 1 and 2 are true. That would be answer choice A. Next up, altitudes. So in triangle ABC, the measure of angle B is 90 degrees. So we have a triangle like this, and BD is an altitude of the triangle. So an altitude is just a sign that connects one of the vertices of the triangles, that's like one of the corners, to the side across from it, such that it creates a 90-degree angle, or it's perpendicular to that side. So it's not necessarily the midpoint. Like, imagine the triangle that's super skinny. The altitude would be down here, right? Because that creates a 90-degree angle. Definitely not the midpoint. So when the SAT uses the word altitude, generally it's referring to this altitude of a right triangle. The length of BC is 10, and the measure of ABD, so that's this angle right here, is 60 degrees. So what is the length of this side right here? And so this angle over here is 60 degrees. This angle over here is also 60 degrees. And this angle over here is 30 degrees. This angle over here is also 30 degrees. And there's a better explanation of why that is in my book, SAT Math from the Ground Up. If you want the longer explanation, go there. We're just going to sort of take this for granted. And so what you'll notice is we have broken this down into a bunch of 30, 60, 90 triangles. And hopefully you know that 30, 60, 90 triangles have a certain relationship on your formula sheet. The 60 to 90 side, if we label that x, then the hypotenuse is double that, and the other leg is that times rad 3. And you can prove why this is true using sine, cosine, and tangent, but we're not going to do that. We're going to take this for granted because this is on our formula sheet. You don't need to memorize it. It's literally given to you on the SAT. So in this triangle down here, the 30-60 side, that's the hypotenuse of this bottom triangle, is 10, which means that if 2x is 10, then this side, the 90-60 side, has to be half of that, has to be 5. And that means this other side has to be 5 times rad 3. Now we can do the same thing, but for this top triangle, I'm going to try to outline this in green, right? This top triangle, where the 60-90 side is 5 rad 3. So that's like your x, which means the side that we're trying to solve for, AD, this pink side, has to be that times rad 3. So this is 5 rad 3 times rad 3, which is the same as 5 times 3, which is the same as 15. And so that's your final answer. So if you know what you're doing, altitude problems seem very easy. I promise you, if you didn't make the connections that I just made right here, this problem is a lot harder to do. They can also be a little harder if you're forced to focus on the ratios between sides as opposed to solving directly for the sides. So there's a lot that you can expect to see. I just wanted to integrate 30, 60, 90 triangles into a problem because they do come up and come in handy sometimes on the SAT. Okay, next we've got this problem dealing with the circle formula. So first things first, you should know what the circle formula is. It's x minus h squared plus y minus k squared equals r squared. The irony of this problem, and I should probably change the name to take out the formula part, is you actually don't need the formula for this problem. The way the SAT might want you to solve this is they would want you to complete the square and rewrite this into HK form so that you can easily identify what the radius is and what the center is. However, we can completely get around that in Desmos. So what we're going to do is we're going to take this equation. Well, we're going to clear Desmos, so you can go to settings, delete all. It's the fastest way to clear your sidebar. And now we can type in the equation verbatim. I don't know how I did that. We can type in the equation verbatim into Desmos. Oh my god. Maybe I can't type. Type in the circle verbatim into Desmos, and we get the circle. And if you wanted to figure out the center or the radius of the circle, one thing that you can do for the center is you can take these 2 points and manually find the midpoint or manually calculate the distance just by looking at this. 4 is 10 above -6, so the diameter is 10, so the radius is 5. But if I'm lazy and I don't even trust my own arithmetic, I can copy these points down. I can label them, like I'm going to label them A and B, like this. And then I can do, if I want to find the diameter, that would be the distance between A and B. So I can use this distance function like that, and I get 10. So the radius has to be 5. And if I want to find the center, I can do the midpoint of A and B, which gives me -3, -1. So these are just nice little functions that you can use on the SAT. They're not terribly useful because like 4 minus -6 is not a hard thing to do, but you know, whatever. So when we have a line that is tangent to the circle, basically what that means is that the line touches the circle, but only at one specific point. And this point has to be perpendicular to the radius. There's no other way that we can draw a line that only touches the circle at one point and have it not be perpendicular to the radius. And so we're told in the problem that this tangent line has a slope of 3/4. And so if this is a slope of 3/4, then this radius has to have a slope of -4/3, at least the specific radius that goes from the center to this point A, B, where our tangent line touches the circle. And if you're wondering, how do we know this? It's because -4/3 is the negative reciprocal of 3/4, and any two perpendicular lines have negative reciprocal slopes from one another. So again, this is like really weird to think about. Most people are used to thinking about the radius as a distance because the radius itself is indeed a distance, but we are concerned not with the length of the radius, but we're concerned with its slope of -4/3. So now the question is, how do we find AB given this information? Well, think about what the slope actually means. When a slope is -4/3, that means that the rise over the run, the change in y over the change in x, has to be -4/3, which means our y goes down 4 units for every 3 units that we go to the right. And yes, I did contrive this problem so that going down 4 and right 3 will take you directly to the point AB. If you really wanted to, you could like run a regression, figure out the equation of the line, and then figure out where that line has to touch the circle. But we're not going to do all that. All we care about is the fact that when we go down 4 units and right 3 units, we perfectly reach the point A, B. So when we go down 4 units, that means we get a B value of -5, right? That's -1 minus 4. And then when we go right 3 units, that gives us an A value of -3 plus 3, which is 0. And so the point AB is 0, -5. The question's asking for the value of B, so we would say -5 is our final answer. And so unlike some of the previous questions, this exact format has not been asked before, at least to my knowledge on past SAT. But I think I've designed this problem such that like if you're comfortable with this problem, you're in good shape for SAT tangent line problems. And if you're not comfortable with this, then you're not in good shape. So yeah, College Board loves pyramids. They love pyramids more than the Egyptians do, I swear to God. And in this case, I've decided to make a pyramid problem that I honestly think is a little harder than what you're probably going to see on the SAT. But I don't know. They got to do something weird because they've kept asking like the same pyramid problem 5 times, so that they're going to switch it up at some point. And I think this is a reasonable way that they could switch it up. So first things first, consider a square right pyramid with a volume of 400 cubic inches. So the volume of a pyramid is 1/3 length, width, and height. Think of it as like a rectangular prism, but we just like cut it into 1/3 because like, I don't know, triangles and stuff. I mean, there's not really an intuitive explanation. This is on your formula sheet, just refer to it. And a slant height of 13 inches. If you don't know the difference between the height of a pyramid and the slant height of a pyramid, you're screwed on pyramid problems just right off the bat. So pyramids look like this. They have a square base. Oh, that's a pretty horrendous drawing. Okay, wait, let me spend like 5 minutes trying to draw a pyramid. Okay, wait, this one is, no, this one sucks. I promise you this is harder than the SAT math for me. No, I can do better, hold on. Okay, this is, fun fact, if you join my SAT Math Masterclass, it's actually just me drawing pyramids for 2 hours. Okay, I figured it out. I think this one's pretty solid. We're gonna go with this one. So the height of the pyramid is the distance from the top of the pyramid to the base, just like that. That's going to be your height. The slant height of a pyramid, on the other hand, is like the distance to climb up the side of the pyramid. If you feel like doing that in Egypt, go for it. And they're connected by 1/2 of the base. So like if this is your base, then the line that connects the height, the bottom of the height to the bottom of the slant height would be 1/2 of the base. And this creates a nice right triangle that you can do the Pythagorean theorem with. So if you don't know this, you're cooked on every single pyramid problem. And if you do know this, you can at least start these problems. So the slant height in this case is exactly 13 inches. The pyramid's length, width, and height are all integers. What is the surface area of the pyramid in cubic inches? So this problem already looks unsolvable, right? Like, how are we supposed to get the surface area just by using the slant height and the volume? Like, there's no way this is possible. It actually is, and we'll take a look at why. So first, let's think about what the surface area actually is, what we're solving for. Surface area formulas on the SAT are not worth memorizing, they're worth understanding. You need to be able to derive them on your own, because you're gonna get weird situations like rectangular cubes with their tops missing, or like glued together cubes. So, and these are going to affect your surface area, so you need to be able to figure out these formulas on your own. So in this case, for this pyramid, our surface area consists of first the square base. So the square having some base length, I'm going to call b. We'll do b squared, because that's length times width when your length and the width are the same. And then we also want to add these triangular faces. So each of these triangulars has a formula of 1/2 base times height. The base is indeed the base, but the height is not the height of the pyramid, right? The height of these triangular faces is the slant height of the pyramid. So it's actually 13. This right here is a huge mistake that plenty of students are going to make. Is they're going to see height and they're going to put an h, and they actually aren't referring to this h, they're referring to this h, and everything goes wrong. So make sure you're very deliberate. It is the 1/2 times the base times the slant height. And so this is what we're solving for. We're solving for b squared plus 1/2 times b times 13. Sorry guys, future me has to come back because I realized I just did not include a 4 here. This is 1/2 base times 13 gives you the area of one of these triangular sides, but there are 4 of them. So you have to multiply this by 4. So for the rest of this problem, this 4 is going to be missing, but I promise you there's a 4 there. So if we know the base, then we know the surface area of the pyramid. And this is a good observation to make. So now there's a question, okay, how do we figure out the base? Well, we have this volume formula, right? So we know that the volume is 400, and we know that that equals 1/3 length with height. So the length and the width we've already determined are just b's. So we have bb height, and so we can write this as b squared times height. We don't know what the height is, but this is an equation that we have. I'm going to label this as equation number 1. And then the question is there a second equation that we can come up with? Because if we have a second equation with something something base, something something height, then we have a system of equations, and we can solve for base, and we can plug that in here, and we can figure out surface area, and everyone's happy. So if we look at the paragraph, we don't see any other information. But remember this right triangle from 2 minutes ago? This right triangle can come in handy, where we have a second equation. We can say 1/2 times base squared, that's like your bottom leg, that's the screen side, plus your height squared, equals your slant height squared, 13 squared. Sure enough, this is another equation that involves your base, involves your height, and nothing else, which means now you have a system of 2 equations. And this is a pretty gnarly system to solve by hand, so we're not going to do that. In fact, you should never solve a system by hand on the SAT, because Desmos is always here. We're going to go into Desmos, we're going to clear everything. We're going to type in 400 equals 1/3 x squared y, and 1/2 x, parentheses, make sure to have your parentheses, squared plus y squared equals 13 squared. Notice I'm not using h and b, I'm using x and y, because h and b are recognized as constants by Desmos, x and y are recognized as variables, which means they're actually going to graph. And we get this super weird thing where one of these equations is a circle or an ellipse. Like this makes no sense conceptually. How is this a Pythagorean theorem? It's weird. Math is weird sometimes. But the point is, if we want to figure out our base we decided was x, right? So we want to figure out the x coordinate of these solutions. Now notice, we have a couple of options to choose from, right? There are 4 points of intersection. This is why I included this tiny word that says they're all integers, right? So if they're all integers, this eliminates that point and that point, because those bases and heights are not integers. So we have negative 10, 12, and 10 and 12. Hopefully you guys know which one's the correct one. It would be 10 and 12. Why? My base cannot be negative 10 inches long. That's just not a valid unit of measurement. And so now we have a base of 10. We can plug in that the surface area is 10 squared plus 1/2 times 10 times 13 times 4, which gives you 100 plus 260. Please use your calculator. Don't try to do this in your head. And you'll get a surface area of 360 inches squared. I know it says cubic. That's a typo. It should be square inches because it's surface area, but whatever. And finally, if you haven't jumped out your window yet, number 24, frequency chart analysis. So Desmos loves frequency charts. They also love asking about mean, median, range, and standard deviation. So why not have a question that asks about all 4 of them? So dataset A is summarized by this table, and dataset B is created by multiplying all of the values in dataset A by 2. So when I say values, I'm not saying frequency. For some reason, a lot of people look at frequency charts and they think that multiplying the data by 2 means multiplying these frequencies by 2, but that's not what I'm saying. This frequency chart as a data set, like if I wanted to write it out, would be 2 1s, 5 2s, 6 3s, etc., right? And so if I double all the values, that means these values are going from 1s to 2s, 2s to 4s, 3s to 6s, etc. Just make sure that you understand this is not the data. This is the data that you're concerned with. So data set B would look like this. We have values 2, 4, 6, 8, 10 now, and the same exact frequencies occurring. So we still have this sort of symmetric distribution, just now our points are at 2, 4, 6, 8, 10 instead of 1, 2, 3, 4, 5. So let's evaluate these. Number 1, the difference between the mean and median of data set B is 0. So I'm sure a lot of people are going to be tempted to go into Desmos and plug in your mean, plug in your median, and then subtract them. Don't do that. It's just time consuming to actually compute the mean and median of this. The frequencies 2, 5, 6, 5, 2 are perfectly symmetric. We can think about this graphically. A frequency chart as a table would look like this. And this is perfectly symmetric. So your median, which is the middle of the data set, should be at 6. Hopefully it's intuitive why that's the case. For a symmetric data set, we can think of like cutting off this end means cutting off that end. But then the mean should also be at 6. In my book, SATMath from the Ground Up, I explain this as the mean is like the fulcrum of a balance scale. This little triangular piece, if you imagine your number line as a balance scale, where all of your data is like a bunch of rocks on the scale and you're trying to keep it completely balanced. And your fulcrum has to be positioned at the value, in this case 6, that would make the scale perfectly balanced. So it's not lopsided like this or this. And so if you think about a symmetric data set, hopefully it's intuitive why your fulcrum has to be right in the middle at 6. So the fulcrum represents the mean, and 6, as we know, represents the median or the middle. And if the mean equals the median, then the difference between the mean and median is 0. Definitely does have to be true. It's true in dataset A, it's still true in dataset B. Next up, we have number 2. The standard deviation of dataset B is equal to the standard deviation of data. So the standard deviation, you don't need to know how to calculate it on the SAT. You just need to know that it represents the spread of the data. So if the data is more spread out, that means that the standard deviation is higher. In this case, the data is more spread out, and it doesn't look like it, right? Visually, it's like, okay, this distribution and this distribution look the exact same. But if you think about what's actually happening, there are more points in between each of these that weren't there before. And so think of these as like 5 different towers that in dataset A were all right next to each other. They were all like bordering each other. And now we're adding some space in between each tower. And so the values are getting farther from the mean. They're getting farther from the 6. We have 2 instead of 1. That's a difference of 4 as opposed to a difference of 2. And so your standard deviation is indeed increasing in dataset B. So we would say they're not equal to each other. And finally, the range of dataset B is double the range of dataset A. So the range, this is probably the easiest one to answer, we can calculate by taking the maximum value and subtracting it by the minimum value. 10 minus 2 is 8 in dataset B, and then 5 minus 1 is 4 in dataset A. So sure enough, the range is indeed doubled when we double all of the values. In fact, the mean, median, range, and I believe standard deviation are all doubled exactly if you double every single value in the dataset. That's not something you need to know, but I think it's good to be able to think through that and why that might be the case, because the SAT will often ask you to add another value to the data set or manipulate the data in some way. And they'll ask, how does this affect the mean or the median or the range or the standard deviation? So in this case, we have 1 and 3 being true. So answer choice C. If you've made it to the end of the video, thank you so much for watching. I understand my upload schedule is terrible, but you guys got to understand, I'm a full-time student. I'm a software engineering intern. I tutor, I run the group class, I wrote this book. I've been playing Minecraft. This is my camel Alfonso. So, you know, so many responsibilities, all of equal importance, but I'm trying to upload more. In the meantime, since you've made it to the end, I'm sure you're a great fit for the SAT Math Masterclass, and if not, you can always check out my book where I've distilled all the topics in the masterclass into about 200 conceptual questions. And regardless, thanks for watching, and I'll see you in the next one.